You've probably seen it at least once, even if you didn't think much of it at the time. A single ant, moving in a strangely deliberate, almost comical way, hoisting a piece of leaf many times her own size above her body like a tiny green sail, following a trail of dozens of others doing exactly the same thing, all of them heading in the same direction, toward a hole in the ground you may not have even noticed was there. Most people watch this for a few seconds, decide it looks vaguely threatening to the garden, and either walk away uneasy or start looking for a way to stop it. After all, an ant stripping leaves off your plants sounds like exactly the kind of pest problem you're supposed to deal with quickly, before it spreads. Except, is not eating your leaf. She has never eaten a leaf in her entire life, and neither has a single member of her colony, going back tens of millions of years. What she is actually doing, and what she is building beneath your feet at this very moment, is one of the most sophisticated agricultural operations in the natural world. A system so advanced studying it have described it, without exaggeration, as one of the only examples of true farming outside of human civilization. Today, we're going underground, into a structure most people will never see, to understand exactly what that leaf is actually for, and why the ant carrying it deserves a great deal more respect than a reflexive stomp. Let's start by correcting the assumption almost everyone makes the first time they see this behavior. Leafcutter ants, the ants responsible for this exact scene, do not eat the leaves they cut. Not the fresh green fragment she's carrying above her head, and not any part of the plant material her colony collects, ever. Leafcutter ants, most commonly species in the genera Atta and Acromyrmex, found across the southern United States and throughout much of Central and South America, cut and transport plant material for an entirely different purpose. The leaf fragment is not food. It is raw material, harvested and carried back to the nest to be used as a growing medium for something else entirely, a living organism the ants have been cultivating, protecting, and depending on for their entire existence as a species. That organism is a fungus, and the relationship between this fungus and the ant colony that grows is not a loose or incidental one. It is one of the oldest, most complete examples of agriculture found anywhere in nature, predating human farming by an estimated 50 million years or more. Long before the first human civilization planted the first deliberate crop, leafcutter ants had already developed a fully functioning farming system, complete with cultivation, fertilization, pest management, and even a form of quality control, all coordinated across a colony that can number in the millions. Beneath the visible trail of leaf-carrying workers lies a structure that would be genuinely difficult to believe if it weren't so thoroughly documented by researchers who have spent years excavating and mapping these colonies. A mature leafcutter ant nest can extend many feet below the surface and span an area larger than a typical suburban backyard, containing anywhere from hundreds to, in the largest documented colonies, several thousand interconnected chambers. Some of these chambers serve as nurseries for developing brood. Others serve as waste disposal sites, kept carefully separate from the rest of the colony to prevent contamination. But the majority of the colony's effort and space is devoted to a specific type of chamber, the fungus gardens. Inside each of these chambers, ants maintain a soft, spongy mass of cultivated fungus, grown specifically on a substrate of chewed and processed leaf fragments. The leaf carried above ground is only the raw material. Once it reaches the nest, an entire assembly line of specialized workers takes over. Smaller ants clean the leaf fragment of any surface contaminants and further shred it into smaller pieces. Even smaller workers chew this material into a fine pulp and carefully press it into the fungal mass, essentially planting and tending a crop bed the way a human farmer might prepare and enrich soil before a new planting. The fungus itself, cultivated exclusively by these ants and found essentially nowhere else in nature outside of their nests, grows into small, nutrient-dense structures the colony harvests and feeds to its larvae, and in many species, to the queen herself. In a very real sense, the leaf you saw an ant carrying was never the meal. It was the fertilizer for a crop the entire colony's survival depends on. The relationship between leafcutter ants and their cultivated fungus is not a casual one, and it is not something either species could simply walk away from. Genetic research comparing fungus farming ant species with the specific fungal strains they cultivate has revealed something remarkable. The ants and their fungus have been co-evolving together for an estimated 50 to 60 million years, with certain fungal lineages found exclusively within ant colonies, no longer able to survive or reproduce independently in the wild outside of a nest at all. This is not a relationship of convenience. It is closer to full domestication, mirroring, in almost every meaningful respect, the relationship between humans and the crop species we've cultivated for thousands of years, crops that have similarly become dependent on human cultivation for their continued propagation. The fungus provides the colony's primary food source. The colony provides the fungus with a stable, climate-controlled growing environment, a constant supply of fresh substrate, and active protection from competitors, and in exchange, neither species could easily survive without the other at this point in their shared evolutionary history. When a young queen leaves her natal colony to found a new one, a moment of profound vulnerability we've discussed with other social insects on this channel, she does something extraordinary before she ever leaves. She carries a small starter culture of the colony's fungus, tucked into a specialized pouch in her mouth, on her nuptial flight. If her new colony survives its first fragile weeks, that tiny fungal sample becomes of an entirely new fungus garden, meaning every leafcutter colony in existence today, in a very literal biological sense, propagating a fungal lineage that has been passed queen to queen, colony to colony, for tens of millions of years without interruption, an unbroken agricultural inheritance considerably older than any crop variety cultivated by humans. Here is where the story becomes genuinely difficult to believe, and it's the detail that convinced entomologists this system deserves called true agriculture rather than simple insect behavior. Just as human crops face contamination from harmful fungi, molds, and pathogens, the ant's cultivated fungus garden faces exactly the same threat, primarily from a specialized parasitic mold that, left unchecked, can rapidly overtake and destroy an entire fungus garden, threatening the survival of the whole colony. Leafcutter ants actively defend against this threat using a genuinely remarkable biological tool. Many species maintain a symbiotic relationship with a specific strain of bacteria living on specialized patches of their own exoskeleton, bacteria that produce natural antibiotic compounds specifically effective against the parasitic mold that threatens their fungus crop. In effect, the ants carry their own living pesticide factory on their bodies, cultivated and maintained through the same long evolutionary partnership that produced the fungus farming behavior itself. Worker ants regularly groom this antibiotic-producing bacteria onto the surface of the fungus garden as a preventive measure, and researchers studying this system have specifically cited it as a compelling natural example of sustainable, targeted pest management, developed and refined over a timescale that dwarfs the entire history of human agricultural pest control by tens of millions of years. Beyond the bacterial defense, the colony also practices something that closely resembles active crop inspection. Specialized workers patrol the fungus gardens continuously, physically viewing any sections showing early signs of contamination, isolating and disposing of compromised material in dedicated waste chambers before an infection can spread to the healthy portions of the garden. A level of coordinated, colony-wide disease management that has no clear parallel anywhere else in the insect world. None of this would be possible without one of the most extreme examples of specialized labor division found in any social insect species, and it's worth understanding just how far this specialization goes. Within a single leafcutter colony, worker ants can vary dramatically in physical size, from tiny workers only a few millimeters long to soldiers many times larger, and this size variation is not incidental. It directly determines the specific job each ant performs within the colony's agricultural operation, in a system entomologists refer to as polymorphism, essentially different physical casts built for different tasks. The largest workers, often called soldiers or major workers, handle the heaviest labor, cutting through tough plant material with powerful mandibles, defending the trail and nest entrance from predators and rival colonies, and clearing physical obstacles from foraging paths. Medium-sized workers make up the bulk of the visible leaf-carrying trail you'd actually observe above ground, cutting smaller fragments and transporting them back to the nest. And the smallest workers, some barely visible without close inspection, perform the most delicate tasks of all, processing leaf fragments into fine pulp, tending the fungus garden directly, and in a behavior researchers find particularly striking, occasionally riding on top of the leaf fragments being carried by larger workers along the trail, specifically to fend off parasitic flies that attempt to lay eggs on the leaf-carrying ants during their exposed journey back to the nest. This entire system, millions of individuals across multiple physical castes, each performing a highly specific role within a horticultural operation, functions with no central authority directing it, no single ant aware of the colony's overall plan, only simple local decision-making repeated across an enormous population, producing a level of organized complexity that continues to be studied as a model system for understanding how coordinated behavior can emerge without centralized control, a question with applications well beyond entomology, including in robotics and network design. Stepping back from the underground farm itself, it's understanding what leafcutter ant activity actually does to the broader landscape they inhabit, because the ecological footprint of a mature colony is significant and largely beneficial. A large leafcutter colony can process a substantial volume of plant material over the course of a year, and the underground excavation required to build and maintain a colony's extensive chamber network moves and aerates a considerable quantity of soil in the process, comparable in scale to the soil-turning contribution of other burrowing animals like earthworms, but concentrated and organized around a single, long-lived colony structure. This soil movement improves drainage, incorporates organic material deeper into the soil profile, and creates microhabitat diversity that benefits numerous other species sharing the same landscape, from smaller insects to soil microorganisms. The nutrient cycling role is significant as well. Waste material from the fungus gardens, rich in the processed byproducts of the ants' agricultural activity, is deposited in dedicated waste chambers, gradually in the surrounding soil with nutrients, slow, localized process that has been shown in areas with established leafcutter colonies to influence plant growth patterns and nutrient availability in the immediate vicinity of the nest over time. This doesn't mean every leafcutter colony belongs exactly where you find it, particularly in cases where an active colony is aggressively defoliating cultivated garden plants or agricultural crops you specifically rely on, a legitimate and well-documented concern in some regions. But it does mean the broader presence of leafcutter ants in a landscape, ecologically speaking, closer to a beneficial, long-term soil and nutrient management system than a simple pest, a distinction worth understanding before deciding how to respond to a trail crossing your yard. If you've found a leafcutter trail on your property, here's a practical way to think through your response. First, identify what's actually being targeted. Leafcutter ants show clear preferences for certain plant species over others, and a trail crossing your yard doesn't necessarily mean your prized garden plants are the target, and following the trail a short distance will usually reveal exactly which plant is being harvested. Second, assess the actual damage level. A small volume of leaf material removed from an established, healthy plant over the course of days or weeks is rarely a serious threat to the plant's overall health. While concentrated, rapid defoliation of a smaller or more vulnerable plant is a more legitimate concern worth addressing directly. Third, use targeted deterrents before broad chemical treatment. Physical barriers, such as sticky tree bands applied around the base of a specific plant you want to protect, can prevent ants from accessing that individual plant without affecting the broader colony or the rest of your garden's ecosystem. Fourth, if a colony genuinely threatens agricultural or high-value plantings, consult a professional for targeted treatment, since broad surface treatments are typically ineffective and often unnecessary against colonies this large and deep, and a professional assessment can determine whether targeted intervention around specific vulnerable plants is sufficient. And fifth, consider simply observing where the situation allows it, because in a majority of residential yards, a leafcutter trail crossing an open area of lawn or harvesting from non-critical vegetation represents a genuinely fascinating, low-impact natural process rather than a problem requiring any response at all. The single ant carrying a leaf fragment across your yard is not performing a random, destructive act. She is one worker within a coordinated agricultural system 50 million years in development, contributing a small piece of raw material to a fungus garden her entire colony depends on for survival. A garden defended by living antibiotics, tended by specialized workers matched precisely to their task by size and role, and descended from an unbroken fungal lineage carried queen across an almost incomprehensible span of evolutionary time. Human agriculture, with all its irrigation systems, crop rotation, and pest management, is, from a certain perspective, simply catching up to a system these ants perfected long before the first human ever planted a deliberate seed. The next time you see that small, leaf-carrying figure crossing your patio or your garden path, know that you're not watching a pest at work. You're watching one of the oldest, most sophisticated farmers on the planet, doing exactly what her species has been doing since long before there were humans around to notice. Have you ever followed a leaf-carrying ant trail to see where it actually led? What did it find? Tell me about it in the comments below. I read every single one, and sometimes your stories become the subject of the next video. And if you've ever wondered what another small creature quietly living in your yard actually knows about your world, I think the next video might surprise you just as much as this one did. Until then, keep watching, keep wondering, and never stop paying attention to the small things.